I've seen that like many of you couldn't finish the homework for chapter 6. So that's why I have extended the due date for chapter 6. So it will be due this Friday, the coming Friday. And I have also assigned homework for chapter 7 as well. So and it is chapter 7 part A. So I have just assigned the problems from section 7.1 and section 7.2. And next week we will have one more homework, and in that homework I will assign problems from section 7.3, and maybe I will also assign some problems from section 8.1 and 8.2. Yeah, it was due last Friday, but many of you couldn't finish the homework for chapter 6. I think because of the exam. So maybe you were busy with the exam preparation. So that's why I extended the due date for chapter 6. Yeah, the chapter 6 is due this Friday. Do you have any question? And some of you worked on the review problems. So I told you that I will give you some extra credit based on your work for the review problems. And I'll add that extra credit with exam on grade, and I will post your exam on grade on Blackboard. And you already had 2 quizzes, so you will have more quizzes. So before the next exam, I'm planning to give you 2 more quizzes. So this week there will be no quiz. Next week I'm planning to give 1 quiz, and I'll give 1 more quiz before the next exam. Yeah, the review was not for grade. I'll give you extra credit for the review. Yeah, for completing it, actually I will decide about that. I think no one completed 100%. Actually, I also do not expect that you will complete the 100% of the review problems. So if you complete at least maybe 60 to 70%, I'll give you 5 credits for that. Yeah, 5 points. But if you complete below 50%, then maybe I will give you 2 to 3 points extra credits. Do you have any other question? Okay. So we were discussing sampling distribution for the sample mean. So sampling distribution of the sample mean for a normally distributed variable. So what does it mean? So that's mean if the population is normally distributed, that's mean our original distribution is normal, the population distribution is normal. So if X is the random variable, so that's mean the distribution of X is normal with mean mu and standard deviation sigma. So if X is normal distribution with mean mu and standard deviation sigma, that's mean variance sigma square. Okay, so I'll post your grade on Blackboard by the end of this week or maybe in the weekend. Okay, so if X is normally distributed with mean mu and variance sigma square, then the sampling distribution for the mean, so that's mean the distribution for X bar will be also normal distribution. So regardless of the sample size. So what is the sample size? It doesn't matter if you know the population distribution, that's mean the distribution of X, and if it is normal distribution with mean mu and variance sigma square, then regardless of the sample size, the distribution for the X bar will be also normal distribution. And we know the mean for X bar. If the mean for X is mu, the mean for X bar is also mu. We already know it, right? This is the expected value of X bar, which is the same of the expected value of X. And the variance of X bar, if you remember, the variance of X bar was sigma squared over n. Sigma squared divided by n. So that's mean the variance will be sigma squared over n. So if X is normal distribution, X itself is normal distribution with mean mu and variance sigma squared, then the distribution for X bar will be also normal distribution with mean mu and variance sigma squared over n. Okay. So here you can see normal distribution for IQs. So this is our population distribution. That's been the distribution for X. So this is the distribution for X. And if you look at the distribution, this is bell-shaped curve. So that's mean, and the mean is 100 and the variance is 16. So this is normal distribution. And we have two sampling distribution. One is with sample size 4 and the other one with sample size 16. So here n is 4 and we considered all the sample mean. So that's mean we considered all the sample and calculated the sample mean for each sample. Then we constructed the distribution for X bar and the distribution will look like this. And here the mean is same. The mean of X bar. So this is the distribution of X bar. This is also distribution of X bar. The difference between these two is here, this is the sample size n is 4 and here the sample size n is 16. Now you can see that this is also normal distribution. And this X bar when n is 16, this is also normal distribution. And the mean are, all the means are same. This is 100, this is 100, this is also 100. The only difference is the variance. So here the variance for the original one, it was 16. Then this variance is sigma square over n. So that's mean 16 over n is 4. So it is 4. Okay, so okay, actually they didn't denote the variance. They wrote as normal distribution mu and sigma standard deviation. Sorry. So this is normal mu sigma. So that's mean 16 is standard deviation. So not the variance. So that's mean, okay, let me erase this one. Okay, so here sigma is 16. Sigma is 16. So actually you can use both notation. You can use either this notation mu sigma or mu sigma square. But here they used mu sigma notation. So that's mean this is mu and this is sigma. So now we need to calculate the sigma for this X bar when n is 4. So the sigma is, actual sigma is 16. So this sigma will be then, this sigma will be, yeah, the sigma for X bar will be then sigma over square root of n. So for this one, the sigma X bar, which is sigma over square root of n. So that means 16 over square root of 4. So that will be 8. So the standard deviation for X bar when n is 4 is 8. And here when n is 16, so the standard deviation will be in this case sigma X bar 16 over square root of 16. So that means 16 over 4, which is 4. So the standard deviation is 4. Now you can see that for X bar, for the distribution of X bar, the mean is same. The difference is the standard deviation or the variance decreased, right? It was 16 for the original one. Now we have 8 because we are dividing the standard deviation by square root of n. So that's mean when we calculate when you construct the sampling distribution, the standard deviation for the sampling distribution will be smaller than the standard deviation of the original distribution. So that's why you can see that the original distribution is spreaded more compared to the sampling distribution. And when we increase the sample distribution, sorry, sample size n equals to 16, then it shrunk more, right? So all the observations are very close to the mean. If we increase the sample size more, then it will be more shrunk. Okay, so now we discuss the central limit theorem, CLT. So what is central limit theorem? Okay, so previously we discussed that if the original the population distribution or the distribution of the original variable is normal, then regardless of the sample size, the sampling distribution for mean will be also normal distribution. Now, so what if the population distribution is not normal? So if the distribution of X is not normal, so previously it was normal. Now, if it is skewed distribution like this, maybe right is skewed or left is skewed, or it could be also Z shape. It could be also like this, or maybe it could be like this. So if the distribution of X is not normal distribution, then what will happen to the distribution of X bar? It depends on the sample size. So for a relatively large sample, the central limit theorem says for a relatively large sample size, the variable X bar is approximately normal. So whatever the distribution of X is, it doesn't matter. If the sample size is large, then the approximate distribution of this one will be normal distribution, normal mu mean and standard deviation sigma over square root of n, or you can write mu mean and standard variance sigma square over n. So X bar is approximately normally distributed regardless of the distribution of the variable under consideration. So we do not know the distribution of X. The approximation becomes better when increasing sample size. If we increase the sample size, this approximation becomes better. Okay. So here we have the relative frequency histogram for household size. And if you at the midpoint of each one, then you can see that this is right skewed distribution. The distribution of household size is right skewed. This is not bell shaped. Now we'll construct the sampling distribution for the mean from this distribution. And here you can see that the sample size is 1000, which we can consider as a large sample size. So it means for 1000 samples of 30 household sizes with superimposed normal curve. Oh, okay, so the sample size is 30, but we considered 1000 samples with 30 sample size. And we constructed the distribution for X bar. And you can see that this is approximately normal, right? The density curve is approximately bell shaped. So that's mean this is approximately normal distribution. Okay, sampling distribution of the sample means suppose that a variable X of a population has mean mu and standard deviation sigma. Then for sample of size n, the mean of X bar equals to the population mean. So we already know that, sorry, mu X bar is always equal to mu. The standard deviation of X bar is, and we also know that sigma X bar is sigma over square root of n. So now if X is normally distributed, so X bar, regardless of the sample size, will be normally distributed. And if X is not normally distributed, and if the sample size is large, then X bar is approximately normally distributed, regardless of the distribution of X. So you should remember these facts. Here you can see the distribution of the variable. This is the distribution of X, which is normal distribution, bell curved, and sampling distribution of X bar n equals to 2. Sample size is only 2, is very small sample size, right? But it's still the distribution of X bar is normal. And sampling distribution n is equals to 10. When n is 10, the distribution of X bar, this is also normal. The only difference is when we increase the sample size, the variation or the variability or the spread decreases. So this is the sampling distribution when n is equals to 30. This is the distribution of X bar. So when X is normal distribution. So what will happen if X is not normal distribution? This one, X is uniform distribution, and this is X is not normal distribution. This is right skewed distribution. So now you can see that when the sample size is small, the distribution of X bar is also right skewed, is still right skewed. But if we increase the sample size, the distribution of X bar becomes approximately normal. And here you can also see that when n equals to 2, the distribution is symmetric, but not bell-shaped, not normal distribution. But when we increase the sample size, it becomes normal distribution, right? And the central limits theorem says the same thing. So regardless of the sample size, regardless of the distribution of the population, if the sample size is large, then the distribution, sampling distribution for X bar will be approximately normal distribution. Okay, so before going over some example, I want to show you the simulation. Okay, so let me pull up this. Okay, anyway. Now we'll go over some example. A variable of a population has a mean of mu is equals to 75 and a standard deviation sigma is 28. So here it said that the population mean is mu is equals to 75 and a standard deviation sigma is equals to 28. Identify the sampling distribution of the sample mean for sample of size 49. So in part A, we need to identify the sampling distribution of X bar, sample mean. So the X is a distribution with mean mu is equals to 75 and sigma is 28 and sample size is 49. Now we have to find the distribution of X bar. So what will be the distribution of X bar? Is it normal distribution or something else? What do you think? So it will be a normal distribution. Okay, so let's calculate the mean mu X bar, which is equal to mu. So that's mean this will be 75. Okay, I'm sorry. Now calculate the sigma. Sigma X bar is sigma over square root of n. So that's mean 28 over square root of 49. So it will be then 4. Okay, so we have the mu and we have a standard deviation. Now we need to determine the shape of the distribution, whether it is normal distribution or something else. So what do you think? It will be normal distribution, the X bar? Anyone? Yes, it will be normal distribution. Why? Because the central limit theorem says that if the sample size is large. Now the question is, how do we know that this sample size is large or small? So how do we determine that? Okay, so the rules of thumb is, if the sample size is 30 or more than 30, actually there is no fixed rule. It depends on the distribution of x actually. Sometimes if if it is less than 30, we can consider the sample size is large. This depends on the population distribution. But the rules of thumb is, if the sample size is 30 or more than 30, we'll consider that sample size as a large sample size. And here the sample size is 49, which is greater than 30. So we can consider 49 as a large sample size. So that means the distribution will be, yeah, you are right. It will be normal distribution with mean mu and standard deviation sigma x bar. So this is 75 and standard deviation is 4. So this is the distribution of x bar. So we know the distribution of x bar, which is normal distribution. Now, what assumptions did we make about the distribution of the variable? Okay, so to determine the distribution, sampling distribution, what assumptions we made? So our assumption is the sample size is large, right? Because the sample size is 49. So that was our assumption. So part C, can you answer part A if the sample size is 25 instead of 49? Okay, so in part C, so if the sample size is 25 now, so can we still say that x bar is normal distribution with mean mu and standard deviation 4? So can we still have this distribution for x bar? So what do you think? Yes or no? Yeah, everything else stays same, but the main important point is the sample size. So when we do not know the population distribution, then you have to always look at the sample size. So what is the mean and what is the standard deviation? It doesn't matter. To determine the shape of the distribution, you have to look at the sample size. Yeah, if the sample size is small, then we do not know the distribution of x bar. We cannot determine the distribution of x bar accurately. But if the sample size is large, that's mean, and in this we'll usually consider 30 or greater than 30 as large. So previously it was 49. So that's why we considered 49 as large, and we have the distribution of x bar is normal with mean 75 and standard deviation 4. But in this case, the sample size is 25, which is below 30, right? So that's mean we cannot consider 25 as a large sample size. So that's why we cannot say that this is normal distribution. Actually, we cannot determine the shape of the distribution of x bar in this case. Okay, we'll go over one more example. According to one study, brain weights of men are normally distributed with a mean of 1.60 kilogram and a standard deviation of 0.13 kilogram. So the mean is mu is equal 1.60 and the standard deviation sigma is 0.13. And the distribution of x is normal distribution with mean mu and standard deviation sigma. Now part A, determine the sampling distribution of sample mean for sample size of 3. Okay, so part A, the sample size n is 3. Now we have to determine the distribution of x bar. And in part B, we have to determine the sampling distribution of X bar when N is 12. Okay, so let's consider one more part here, and let's consider N is maybe 50. So what is the distribution of X bar? So we'll have 3 distribution, right? So what will be the distribution of X bar in case A, and what will be the distribution of X bar in case B, and what will be the distribution of X bar in case C? So what do you think? Is it normal distribution? Yes, sure. Okay, so the idea is, if the distribution of X is normal distribution, then we do not care about the sample size. That means if we know the population distribution, then we do not care about the sample size. So what is the sample size? It doesn't matter. The distribution of X bar will be always normal distribution. But if we do not know the distribution of population, that's when we do not know the distribution of X, then you have to look at the sample size. So in this case, X is known, right? We know the X is normal distribution. But if we do not know the distribution of X, in that case, to determine the distribution of X bar, we always have to look at the sample size. If the sample size is large, then we'll consider the X bar is normal distribution. Large means 30 or greater than 30. But if the sample size is small, that means below 30, then we cannot determine the distribution of X bar. Is it clear, or do you have any question? Okay, that's good. Yeah, now, okay, so now what will be the distribution in case A? And what will be the distribution of X bar in case B and in case C? Okay, great, thank you. So what do you think? Anyone? So what should be the distribution of X bar in A, in part A? Okay, so let's go one by one. Oh, to find X bar, yeah, X bar you already know. X bar is the sample mean, right? So 1 over n sigma of xi. But here actually we do not need to calculate X bar. We just need to talk about the distribution of X bar. Yeah, sigma over square root of, yeah, sigma over square root of n is the standard deviation for X bar. Yeah. Okay, so I can just tell you the mean and standard deviation for X bar. Yeah, the mean mu X bar is, I'm sorry, exactly equal to mu, and sigma X bar is sigma over square root of n. Yeah, this is the formula to calculate the mean for X bar and standard deviation for X bar. Yeah. Okay, so what will be the, so do you think that the distribution of X bar in part A will be normal distribution, or it will be something else? So what do you think? Okay, so you are saying it will not be, it shouldn't be a normal distribution, right? Okay, so if you think that X should be normal, X bar should be normal distribution, then write yes. If you think that X bar shouldn't be normal distribution, then you can type no. Okay. Yeah. So all of you say no. Okay, that's great. Yeah. So you looked at the, I think you looked at the sample size, right? The sample size is very small. Okay, but be careful. So when do we look at the sample size? In case, if we do not know the distribution of X, but in this case, do we know the distribution of X? Yes, we know the distribution of X, right? X is normal distribution. So that's mean because it says that according to a study, the brain weights of men are normally distributed. So we have this information. So whenever we have this information that X is normal distribution, we do not need to look at the sample size. So whatever is the sample size, it doesn't matter. X bar will be always normal distribution. If the original distribution is normal distribution, then X bar will be always normal distribution with mean mu, which is 1.6, and standard deviation sigma over square root of n, 0.13 over square root of 3. Similarly, when n is 12, we are not going to look at the sample size at all in this case, because we know that this is normally distributed. The original distribution is normal. So we'll look at the sample size only when we do not know the distribution of X. So this will be also normal distribution, 1.6, 0.13 over square root of 12. And this will be also normal distribution with 1.6, 0.13 square root of 50. Yeah, so all the X bar will be normally distributed with mean mu and standard deviation sigma over square root of n, because the original distribution is normal distribution. Okay, yeah, that's good question. What about if it is not stated that it is normally distributed? Yeah, that's a very good question. Yeah, if it is not stated, that's mean we do not know the distribution of X. So in that case, we have to look at the sample size. So in that case, only part C will be normal distribution because n is 50, right? And in part A and part B, the sample size is 3 and 12, which is very small. So in that case, we cannot determine the distribution of X bar for part A and part B, if it is not stated that the population distribution is normal. Yeah, that's a very good question. Thank you. So is that answer your question? Yes. If it is only over 30 or equal 30, yeah. 30 or over 30, yeah. Okay, great. Let's move to the next example. A population has mean 128 and standard deviation 22. So we are given the mean is 128 and standard deviation sigma is 22. Now in part A, find the mean and standard deviation of X bar for sample size 36. So that's mean we need to find the mu X bar, which is exactly equal to mu 128. And we need to also find sigma X bar, sigma over square root of n. That's mean 22 over square root of 36, 22 over 6. So that's mean it will be 3.67, I guess. Yeah, 3.67. So this is the mean and standard deviation. So we are done with part A. So this is our part A. So in part B, find the probability that the mean of a sample of size 36 will be within 10 units of the population mean that is between 118 and 138. So that's when we have to find the probability that the mean of a sample of size 36, that's mean the X bar. So actually we have to calculate this probability. The mean of a sample size of 36. So that's mean the X bar is between 10 units of the population mean. So that's in the, what is the population mean is 128. So that's mean it will be 118 and 138. So we have to actually find this probability in part B. Okay, so how can we find this probability? So if we know the distribution of X bar, then we can find the probability. If X bar is normal, yeah, then we can find the probability. So what do you think? What will be the distribution of X bar in this case? Is it normal distribution or it will be some other distribution? It will be normal distribution, right? Because we know the samples. We do not know the distribution of the population, but we know the sample size, which is 36, which is large, right? So that's mean it will be 128 and 3.67. Now we need to find this probability. So how can we find this probability? Yes, this is normal distribution. Yeah, that's correct. Thank you. So now we need to find, we have to find the probability. So how can we find the probability? So we know the distribution of X bar, normal distribution. Now we have to find the probability where X bar is between 118 and 138. So to find the probability from normal distribution, first we need to standardize the X bar or X. Then we can calculate the probability. So first we need to convert X bar in its standardized form. So that's when we have to find the z-score, right? We have to write this one in terms of z. So how do we calculate the z-score? So when X is normal distribution, the z-score is X minus the mu over sigma. But now we have X bar, we do not have X. So in case of X bar, the z-score will be X bar minus mu and the standard deviation sigma over square root of n. So this is the formula for the z-score for X bar. So that's mean 118 will become X bar minus mu. So 118 minus mu is 128. And sigma over square root of n, we already calculated, this is 3.67. So it will be divided by 3.67. And similarly, we need to convert this one to z-score. So that's mean 138 minus 128 divided by 3.67. Okay, so now simplify the first one and also simplify this one. Then you will get this 2 z-score. So what is the z-score for the first one? Okay, so this is 118 minus 128 and divided by 3.67. So it will be negative 2.72. Yeah, negative 2.72. And what is the z-score for this one? This will be positive 2.72, right? Yeah, now to find the probability, you need to look at this z-score and this z-score. So first you will look at 2.72 and you will get a number from the table. And then you will look at negative 2.72, you will get another number from the table. So you will take the difference of these two numbers. That will be the probability. So you calculated it 0.0033. Okay, so let me check. So let me look at the Z table. Yeah, so let me share the Z table with you. So can you see the Z table? So negative 2.72. So this is negative 2.7. And second digit is 2. So this is 0.02. So negative 2.72 is here. Yeah, this is 0.0033. Yeah, so if you look at negative 2.72, this is 0.0033. Okay, but we have to find the area between negative 2.72 and positive 2.72. So now we have to also look at positive 2.72. So where is 2.72? 2.72 is 2.7. Yeah, this is 2.72. 0.9967. Okay, so we have 0.0033 and 0.9967. So the area will be then, okay, the area will be then the difference between these two. So 0.9967. Okay, so let me write down here. Okay, so we found 0.9967 and minus 0.0033. So if we take the difference of these two numbers, then it will be 0.9967 minus 0.0033. So it will be actually 0.9934. So the answer will be then 0.9934. Sorry, 99, not 38. It should be 34. So 0.9934. Yeah, so for negative 2.72, yeah, that's correct. This is 0.0033. But we have to find the area between these two numbers, right? Negative 2.72 and 2.72. So if you look at 2.72, it will be 0.9967. And for negative 2.72, it is 0.0033. So we have to take the difference of these two numbers, and that will be 0.9934. So the final answer will be 0.9934. Do you have any question? Yeah, 0.9934. That's correct. Thank you. Okay. The next one is a population has mean 73.5 and standard deviation 2.5. And here we have also the mean is mu is 73.5 and sigma is 2.5. So in part A, we need to find the mean and standard deviation of X bar. So we need to find mu X bar, which is mu. So that means 73.5. And sigma X bar, which is sigma over the square root of n. So that's mean 2.5 over square root of 30. So it will be 2.5 by square root of 30. So it will be 0.4564. So this is 0.4564. Yeah, it looks like 9. Yeah, so 0.4564. Yeah, that's the probability point. Yeah, that's the probability 0.9934. Yeah, for the previous one, the probability was 0.9934. That's correct. Yeah, so we have the mean and standard deviation. Now we need to find the probability that the mean of a sample size 30 will be less than 72. So in part B, we have mean of sample size 30. So we have sample size n equal 30. Now we need to find the probability where mean the X bar is less than 72. We need to find this probability. And similarly here, we have to convert the X bar to Z score. And we know that the Z score for X bar is X bar minus mean divided by sigma over square root of n. So in this case, we have then the Z score is less than 72 minus mu. Mu is 73.5. And sigma over square root of n. We already calculated this one. And this one is 0.4564. So that's mean probability of Z less than. So if you simplify this one, 72 minus 73.5 divided by 0.4564, which is negative 3.287. Negative 3.287 or 29. We can say negative 3.29. So now we have to look at negative. So since this is less than type, if you just look at negative 3.29 on the Z table, you will get the probability. So negative 3.29. So negative 3.2 and 9. So it is 0.0005. The probability is, if you look at the Z table, then the probability will be 0.0005. Yeah, this is the probability. Okay, so we have one more problem here, and this is similar type of problem. A population has mean 48.4 and standard deviation is 6.3. So we have to calculate in part A, we have to calculate mu X bar, which is 48.4, and sigma X bar, which is sigma over square root of n. So that's mean 6.3 over square root of 64. So it will be then 6.3 over 8. So 6.3 divided by 8. So it will be then 0.7875. And in part B, we have to find the probability where probability of X bar is less than 46.7. So you need to calculate the Z score and then look at the Z table, and you will get the probability. Okay, so that's all about chapter 7. So do you have any question? Okay, thank you. So if you do not have any question, we will move to the chapter, move to the next chapter, and which is chapter 8. Okay, thank you. So chapter 8 is about confidence intervals for one population mean. So what does it mean by confidence intervals for one population mean? Okay, so one population mean. That's good. That mean for a single population. So that's mean we'll collect data from a single population. So if we collect data from single population and we have just one population, so the mean for one population will be mu, right? The population mean is mu. So now we have to find the confidence intervals. So what does it mean by confidence intervals? So you know about intervals, right? So did you hear about the intervals before, or confidence interval before? So we know the interval. Interval means we will have two numbers, right? This is the starting point, this is the end point. So for example, if we have 2 to 10, so this means this is an interval. That means all the numbers between 2 and 10, right? Yeah, intervals are in number line, you can just consider the numbers between two numbers. Yeah. Now the question is, what is confidence interval? So the confidence interval means we'll have confidence level. So that's mean we'll construct an interval for mu. Okay, so mu is a parameter and this is unknown. This is called a parameter. This is a parameter and this is unknown. Usually mu is unknown. So we do not know the value of mu. So we do not know the value of mu. So what can we do? We can make inference about mu based on the statistic, right? So what statistic we can use to make inference about mu? Mu is the population mean, right? This is parameter. And to make inference about mu, we can use X bar, the sample mean. We can use X bar. So mu is a single value, single parameter, and we can estimate mu using X bar. And X bar is also a single value. So we can estimate using X bar. Since X bar is a single value, this is a point, right? A single value means a point, a single point. So this type of estimate is called point estimate. So this is called point estimate of mu. So X bar is a point estimate of mu. Okay, so instead of estimating mu using X bar with a single point, we'll estimate the value of mu with an interval. So why do we use interval? Because if you just take a sample from the population and calculate the sample mean, so actually that sample mean doesn't always represent the population mean very well. So for example, if you want to know the class average or the average exam, okay, for example, so you have already taken the first exam 1, and we know the class average, right? So we know the class average is 81 point something. So for the first exam, the class average was 81 point something. So if we consider all the students in our class as a population, then that average will be the population mean, right? So the class average for the first exam was, for example, consider this is 81.5. So this is our class average. So this is the population. If we consider our class as a population, all the students in our class as a population, then the population mean is 81.5. Okay. So now we do not want to ask all the students about their score and calculate the average score. So what we can do instead of doing that, so we have 134 students in our class. So if we ask everyone, it will take more time. So to save the time, what we can do, we can randomly select 10 students or 20 students, and we can ask them about their score, class score, exam score. So we can calculate the average for these 20 students, and that will be X bar. So for example, at first we considered 10 students randomly, and we found the sample mean is 75. Then we collected another sample, and we found the sample mean for second sample is 95. And the average for the third sample is maybe 82. And average is maybe 81.5. Yeah. Here the problem is, when we consider sample and we estimate the sample mean and we make inference about the population mean, that inference may not be a very good inference, because for one sample we found that the sample mean is 75. It doesn't really represent 81.5 very well. And for another sample we found 95. And for example, if we find the sample average for one sample is maybe 50. So based on this, if we make inference about the population, that inference is not an appropriate inference. So what we can do, instead of making inference about the population mean with a single point, we can construct an interval. So maybe the interval is from 70 to 93. So what we are saying now, we are saying the population mean, this interval contains the population mean. That's mean the population mean will be between 70 and 93. That's very good inference, right? We have like very good idea about the range of the population mean. And previously we were just making inference based on a single point. So if we say actually it was 81.5, but if we collect a sample and the sample mean is 50, then 50 really doesn't represent 81.5, right? So that's why we need to construct an interval. This interval is called confidence interval. And there is also chance that we might do mistake, but how much error we might have some error, but we will determine how much error we'll tolerate. That is called the level of significance, and level of significance is denoted by alpha. This is called ALPHA, alpha. So maybe we can consider 5% of error. We can tolerate 5% of error, or we can tolerate 10% of error. And in that case, if we just tolerate only 5% error in constructing the confidence interval, then this is called alpha is 5%, and this is the level of significance. Okay, so now, and there is another term which is called confidence level. So what is confidence level? So we are tolerating 5% error. We are not tolerate more than 5% error. In that case, the level of confidence is 1 minus alpha percentage. That's mean the level of confidence will be 95%. Okay, so the relationship between alpha and confidence level, alpha, if alpha is 5%, then the confidence level or level of confidence will be 1 minus alpha. So that's mean that will be actually 95%. So what does it mean? That's mean we are 95% confident that the interval we constructed contains the parameter mu, but we might do maximum 5% error, and this is called the significance level or level of significance. So alpha is actually alpha is also called type 1 error. That's mean the error we can make to construct confidence interval is maximum 5%. Okay, so we already discussed the point estimate. That's mean if we estimate the parameter with a single value, that is called point estimate. Now confidence interval estimate. So we need to know the confidence interval, which is CI, an interval of numbers obtained from a point estimate of a parameter. So that's mean we'll obtain an interval from the point estimate of a parameter. Then confidence level, the confidence we have that the parameter lies in the confidence interval. So that's mean how much confident we are that the parameter is in that interval. That is called the confidence interval. And confidence interval estimate, that's mean the confidence level and confidence, will construct the confidence interval. Okay, so now here you can see 25 confidence interval for the mean price of all new mobile homes. So we have the data for mobile homes, and we collected 25 samples with sample size 36. So our sample size was 36, and we collected 25 samples, and we calculated the sample average or sample mean for each one, and it was 65, 64 for the second one, 64, like this. Then we constructed the confidence interval for each sample. Our population mean was mu, which is 65. Now we'll construct an interval for mu. So for the first sample, we construct an interval. We found that this is 63 to 67, 63.05 to 67. And this is the first interval, this is second. So we constructed 25 intervals. Now you can see that only one interval didn't cover the population mean, but all the intervals contain the population mean mu. So that's mean we said that, and this is 95%. So that's mean we are 95% confident that the interval contains the population mean. So there is only chance that we might make 5% error. And you can see that out of 25 intervals, only one interval doesn't contain the population mean. So we constructed 25, and only out of 25. So how much error we made here? 1/25. So that's mean only 4% error. Okay, so now the idea is, so to construct the confidence interval, we need to know alpha, and which is 1 minus the confidence level. So if you want to construct 95% confidence interval, then 1 minus alpha will be then 1 minus 0.95. So that's mean 0.05. And if you want to construct 90% confidence interval, then it will be 1 minus 0.1. So that's mean, 1 minus 0.9. So that's mean 0.1. Alpha will be 0.1. If you construct 85% confidence interval, then it will be 1 minus 0.85. So alpha will be 0.15. Okay, so now we'll discuss about how do we construct the confidence interval. What is the formula for confidence interval? So confidence intervals for one population mean when sigma is known. Okay, so actually we'll have several formulas for constructing population mean. It depends on the assumption. So one assumption is sigma is known. We know the sigma value. Usually sigma is unknown, but here we considered the sigma is known. The standard deviation, population standard deviation is known. So when the population standard deviation is known, then the formula for constructing the confidence interval is mu plus minus the alpha over 2 times sigma over square root of n. So when we are saying confidence interval, so that's when we have two numbers, right? We have an interval and we know this number and this number. The first number is mu minus the alpha over 2 times sigma over square root of n. And second number is mu plus the alpha over 2 times sigma over square root of n. So this is the confidence interval, or we can say here, actually this is x bar, not mu, this is x bar. So x bar, this is x bar minus the alpha over 2 times sigma over square root of n, and this is x bar plus the alpha over 2 times sigma over square root of n. So this is the formula to find the confidence interval for one population mean when sigma is known. That means we know the sigma value. And here you can see that this is the confidence interval, 95% confidence interval for all samples and within 2 standard deviations of, okay. So anyway, so here, this is the procedure to construct a confidence interval for one population mean. So one mean, this is called one mean Z interval. And we need to satisfy this assumption if we want to use this formula to construct the confidence interval. So the first assumption is simple random sample. So the sample should be independent. So that's means simple random sample. Second assumption is normal population or large sample. Either the population is normal distribution or large sample, 30 or more than 30. So step 1 and sigma is known. So if we have these three assumptions satisfied, then we can use this formula to construct the confidence interval. So step 1 is for a confidence level of 1 minus alpha, we need to find z alpha over 2. So first, for a confidence level 1 minus alpha, first we need to calculate z alpha over 2. So that's means first we need to find the alpha value and then find z alpha over 2 from the z table. Okay, the confidence interval for mu is, then use this formula to find the confidence interval. This is called the lower limit of the confidence interval. This is called lower limit of the confidence interval, and this one is called the upper limit of the confidence interval. So we have to calculate these two numbers. Okay, so and where n is the sample size and x bar is the sample mean and sigma is the population standard deviation. And step 3 is interpret the confidence interval. This is very crucial. This is very important to know how to interpret because most of the cases we interpret the confidence interval incorrectly. So you have to always interpret this one correctly. Okay, so I'll let you know. I'll tell you how to interpret the confidence interval. Okay, now this is the key factor you need to remember when to use the one mean z interval procedure. So we want to construct confidence interval for one mean, and when do we use the z interval procedure? For a small sample, say size less than 15, if the sample size is less than 15, the z interval procedure should be used only when the variable is normally distributed or very close to being so. So that's mean only when the population distribution is normally distributed and the sample size is less than 15, in that case we can use z interval. For sample of moderate size, if the sample size is between 15 to 30, we consider this sample size as moderate sample size. And the z interval procedure can be used unless the data contain outliers. So if the data doesn't have any outliers or the variable under consideration is far from being normally distributed. What does it mean by far from being normal? Maybe if the distribution is like this. So this is not close to a normal distribution, right? This is very right skewed distribution. So in that case, if the sample size is between 15 and 13 or less than 13, we cannot use z interval procedure. We have to use something else, some other formula. Okay. So for large samples, the sample size 30 or more, the z interval procedure can be used essentially without restriction. So without any restriction, we can use z interval if the sample size is 30 or more. But however, if outliers are present and their removal is not justified, that means if there is outlier and we cannot remove them, then in that case, what we can do, we can construct confidence interval with outliers and without outliers using z interval. And we'll compare these two intervals. We'll see whether we have two very different confidence interval or not. If we have two similar confidence interval, then z interval is fine. But with outlier and without outlier, if we have like two really different confidence interval, in that case, we cannot use z interval. That will be a wrong procedure. And if our outliers are present, but their removals is justified, if we can remove them, then we can use z interval procedure to construct the confidence interval. Okay, the idea is if the sample size is very small, that means less than 15. In that case, we have to If the distribution is normal distribution, we can use Z interval. Otherwise, we cannot use. But if the sample size is 15 to 30, and if the data set doesn't have any outliers and very close to normal distribution, then in that case, we can use Z confidence interval. But for a very large sample, regardless of the sample size, regardless of the sample population distribution, we can use Z interval. But if the data set has outliers and that affect the confidence interval, then we can use Z interval. Okay. So this is actually fundamental principle of data analysis. So what does it mean? That means when you will be constructing confidence interval, when you will be performing hypothesis test. So you will be using some procedure, right? But before doing that, first you need to determine, you need to make sure that the procedure you are using is correct procedure. So before performing a statistical inference procedure, examine the sample data. This is really important. If any of the conditions required for using the procedure, so to use some procedure, use some method, you need to fulfill some requirement. You need to satisfy some condition. If all the conditions are not satisfied, then we cannot use that procedure. In that case, you have to use a different procedure or more appropriate procedure. So that's the fundamental principle of data analysis. So before doing any data analysis, first you need to determine the procedure you are using is an appropriate procedure. Otherwise, your analysis will not be a very good analysis, and the inference you'll be making based on that analysis will be very incorrect inference. Okay, so then we'll discuss about the margin of error for the estimate of mu. Okay, so we know the formula for the confidence interval, which is x bar plus minus z alpha over 2 times sigma over a square root of n. So where this part is called the margin of error, or E. E is the margin of error. So the margin of error is equal z alpha over 2 times sigma over a square root of n. So where z alpha over 2, this part is critical value. This part is called CRITICL, critical value. And this part is called standard error, SE, standard error. So the product of critical value and the standard error is called the margin of error. Margin of error means the error margin of the confidence interval. So that's mean how much error you are making to estimate the mu. And this is called the width of the confidence interval. This is width of the confidence interval. So the difference between the upper limit and the lower limit of the confidence interval is called the width of the confidence interval. And this part is the margin of error. And this part is also the margin of error. So the confidence interval actually x bar plus minus margin of error. And the difference between the lower limit and upper limit. So upper limit is x bar plus E minus x bar minus E. This is the width. This is WIDTH, width of the confidence interval. So now if you simplify this one, then it will be x bar plus E minus x bar plus E. So x bar will be cancelled out. Then we'll have actually 2 times E. So that's mean the width of the confidence interval is 2 times of the margin of error. So sample size and accuracy for a fixed confidence interval increase the sample size, decreases the margin of error, and hence improves the accuracy of the confidence interval. So what does it mean? That's mean, okay, so we know the formula for the margin of error. So the margin of error E is equals to Z times alpha over 2 sigma over square root of n. Okay, so what will happen to margin of error if we increase n? If n increases, then the margin of error will decreases, right? And we know that the width of the confidence interval is 2 times the margin of error. So if the margin of error decreases, that's mean the width will also decrease. So that's mean if n increases, the width of the confidence interval will decrease, and the margin of error will also decrease. So that's when we'll have more accurate means more concise confidence interval. So the confidence interval is x bar plus minus e. If e is smaller, so that's mean the width will have a narrow confidence interval, right? Narrower confidence interval. But if e increases, then we'll have wider confidence interval. So that's mean the accuracy will decrease, and if e decreases, the accuracy will improve, right? We will have narrower confidence interval when e decreases. So there is actually there is direct relationship between e and n. So when n increases, e decreases, and e decreases means the width of the confidence interval will also decrease. That means we'll have narrower confidence interval. And in the next class, I'll show you some computer simulation where we will increase the n, and you will see that the how we'll get the confidence interval. You will see that the when we increase the n, the width of the confidence interval will decrease. And I will show you some computer simulation in the next class. And we'll go over some example. We'll construct confidence interval for x bar. Yeah. So today I will stop here.